All right, everybody, welcome back to class. So today we're going to be covering linear piecewise functions. So for our warm-up, we are going to be looking at this graph that is on the page, and it's a graph that represents the amount of water in a bathtub is shown. So I want you to go ahead and answer these 3 questions, and I'll be back in a second to go over some answers with you. So for number 1, is the relation a function? Why or why not? So if we're looking at this graph, it is a function. So the answer here would be yes. And how we know that is if we were to take this ruler as a vertical line test just by looking at this one side of it. Does the graph hit the ruler at 2 points at any time? And the answer is no. So it passes it passes the vertical line test. Line test. So, and then now we're going to describe the problem situation in each of the 3 pieces. So, we're going to say that in this part is the bathtub is filling up. And it is filling up. So, as time increases, the amount of water in the bathtub increases. And then this is the time at which the bath was taken. And so the water levels didn't change at all. And then this part where it slopes down is when the bathtub was drained. So, and the more time that went on, the less water there was in the bathtub. Now, final question, did the bathtub fill or drain faster? It obviously filled faster because the slope here is much greater than the slope is at the end. So that's how you know, is based off our slopes. Okay, so now we're going to look at some of our learning goals. So this is the goals that hopefully you'll be able to be doing by the end of this lesson. So I can create graph of linear piecewise functions given a scenario. I can write linear piecewise functions from scenarios, tables, and graphs. And then finally, I can compare linear absolute value functions to a linear piecewise function. So on this, just playing some ball, if you have your book, it says that your teacher is going to read a scenario line by line. If you are taking notes and do not have a book, which honestly, I would recommend getting a book. These notes and homework are all going to be in the book. So if you're comfortable using the online textbook, you can keep going, but I would recommend emailing me about getting a book. I just think it's going to be the best option. So on the next slide, there's a graph for this. If you're taking notes on paper, go ahead and graph these scenarios I'm about to tell you. And then if you have a book, you can go ahead and graph it in the book. So Carter and his friends leave school and jog to the basketball court that is about halfway between his school and home. When they get there, everyone realizes that no one brought a basketball. Carter races back to school and gets his basketball from his locker. He then races back to his friends waiting for him. I believe this to be they play basketball for about 45 minutes until they split up to go home. Carter walks partway home and then stops at a convenience store to get a drink. He then finishes his walk home. Okay, I'm going to go ahead and graph my pieces of this scenario. So the first thing I'm actually going to do is label my axis. So my y-axis is going to be my distance from home. And my x-axis is going to be my time in minutes. So the first thing that happened was that Carter and his friends leave school and jog to the basketball court that is halfway between his school and home. So we're going to jog to the basketball court. And then we realize that we forgot the basketball, so Carter races back to school to get his basketball from his locker. So we got to get our basketball from our locker, and then we're going to race back to the basketball court. And then we play basketball for about 45 minutes. So a good little chunk of time there. Maybe even go a little bit more. And then Carter walks part of the way home and then stops at a convenience store to get a drink. So now Carter's walking home, and then we stopped to get our drink, and then we did the rest of our walk home. I'm going to draw that a little bit better. That doesn't look really good. So we're going to start walking home. We're going to stop and get our drink, and then we're going to continue to walk home. So, and then on the next slide, we have a couple of questions, and if you're in your book, they're below your graph. So we're going to answer these questions on our own, so distance learners, go ahead and take a second to answer these. So will everyone in class have the exact same graphs? No. We're all kind of interpreting our time a little bit differently, but they all should have the same general shape. And my slope for the run may be a little bit more than yours. My walk, your walk may be a little bit slower. So what clues from the scenario did you decide how steep to make your lines? So that's where we kind of went off the jog. What are the ones we used? To race and walk. So we were kind of using those terms to determine how steep our slopes were going to be. And then how did you determine the length of each line? So the length of my lines were determined based off other lines. So obviously when we were playing basketball, we were there for 45 minutes. So it's obviously going to be a lot longer than how long it took me to get my basketball or how long my stop at that convenience store was. So, and then if you were in class, we would get in our groups and kind of discuss the answers to these. But we'll kind of discuss them together. So how many segments does your graph have? And what does this indicate about your scenarios? So if we look back at our graph, we have 1, 2, 3, 4, 5, 6, 7, 8. And everyone should have about 8. And so what that is showing us is the different steps in the scenario for how we got Carter to get home. Does your graph have any horizontal line segments? If so, what do they represent? If not, explain. So the horizontal line segments that we have represent when Carter's distance from home is not changing. So yes, we do. And it's when our distance is not changing. Does your graph have any decreasing line segments? And we do, and they represent when Carter is moving closer to home. Closer to home. Sorry guys, I don't have much room on here. Does your graph have any increasing line segments? If so, what does that represent? And there is some, and that's when he races back to school to get his basketball because he's going farther away from home. So when Carter goes back to school. And then what do the X and Y, or the Y-intercept and X-intercepts represent? So the Y-intercept represents how far Carter is from home when the scenario starts. So how far at the start. That is our Y-intercept. And our X-intercept represents the time Carter took to reach his home. So that is our time to get home. Okay, so now we're going to develop a piecewise function from a scenario, and the scenario is listed here. It's listed at the top of the page in your book if you have your book. There is a table we are going to fill out and a graph we are going to fill out on this next page. So I'm going to read the scenario real fast, and then we'll fill in that chart together. So Paulina owns a popular pizza parlor. She noticed a daily trend in her pizza sales. When her shop opens from lunch to 11 a.m., she sells 30 pizzas each hour for the first 3 hours. Sales dwindle to 10 pizzas per hour for the next 3 hours. Business picks up from 5 p.m. until closing time at 11 p.m. when she sells 40 pizzas each hour for all 6 hours. So we are going to go to our next slide, and we are going to fill in this pizza chart. So I'm going to make my pen a little smaller so I can write in there. So number of hours since the pizza shop opened. That's we're just going to kind of count up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Because we're just going up by hours by the times of the day. And for the total number of pizzas sold, we are going to use the information from this slide. For example, when she opens for lunch at 11, she sells pizza for the first 3 hours. So we're going to have 30 pizzas sold an hour. So we're at first going to have 30. And then the next hour, we're going to sell 30 more. So our total is then going to be 60 and then 90. And let's go back, and the sales dwindle to 10 pizza per hour for the next 3 hours. So now we're just going to add 10 in those spots. So this will be 100, 110, and 120. And that was just for the next 3 hours. And then from 5 p.m. until closing time at 11, she sells 40 pizzas an hour for all 6 hours. So this is when we're going to start adding 40 every time. So 120 plus 40 is going to give us 160, 200, 240, 280, 320, and 360. If you were confused about how I got these numbers, go back and reread this a couple times, okay? And it'll explain how we go from each factor to each factor, okay? So now we are going to graph this. I'm going to do the best I can on this little tablet. Here in a couple slides, it's already graphed for me, so please forgive me when it's really bad. So we were constantly going up until 2 p.m. to get us to 90 pizzas. So I'm going to kind of go up here, and 90 is going to be about right here. And we're all going to pretend that that's a nice, pretty straight line. And then this is when we switch to the 10 per hour, and that's until 5 p.m. So this is 5 p.m., and we got up to 120. So again, we're going to pretend that's a nice, pretty straight line. And then after that, until we closed, we sold about 60 pizzas per hour. So we made it all the way up to 360, which is at our very top right here at 12 o'clock. So we're just going to try our best to draw a straight line. Okay, let's all pretend that's straight. I'm working on my penmanship skills on this tablet. So that's roughly what our graphs should look like. So the graph that you created represents a piecewise function. A piecewise function is a function that can be represented by more than one function, each which corresponds to a part of the domain. A linear piecewise function is a function that can be represented by linear functions only, each of which correspond to be a part of the domain. So then we're going to answer a few questions about these graphs. So we're going to identify the domain of this problem. So our domain, and hopefully you remember this from probably last year. So domain, I spelled domain wrong, huh? Domain goes with our x values. So our x values on this graph, we start at 0 and we go all the way until 12, which you can also see that in this chart over here. So, and we are going to include those because we do have values at those specific points. Okay, so then for b, it's just how many pieces make up this function. So we have our piece right here, our piece right here, and our piece right there. So we have a total of 3 pieces here total. It's an ugly 3, I'm sorry guys. Okay, and then what is the domain for each piece? So for our first piece, we're looking at from when 0 all the way until 3. And so that's our first piece. Okay, so how many pieces make up this function? So I'm going to kind of color code these pieces so that we can answer then what is the domain for each piece. So I'm going to give this little piece red, this piece purple, And we'll go in, let's do orange for that last piece. Maybe if my pen would work, we could. There it goes, okay. So orange for that last little piece right there. So total, we do have 3 pieces. Sorry guys, get distracted, can't spell. So in our first piece, which is outlined in that red, the domain, so we start at 0 and we end at 3. So the best way to describe why we include both of those is because when we go back up to our description, we are selling 30 pizzas for each of those hours. So that 3 is included in that first section. So then whenever we're looking at our purple section, which then takes us from 3 to 6. So, and for this section, we are going to include the 6 because, again, we were then selling them for the next 6 hours. So that 6 is included in that one. And then for our third and final piece, we are going from 6 all the way until 12. And we are just including 12 on this one because that's where the values end. And so whenever we're talking about the 0, 3, 3, 6, and 6, 12, we are talking about the numbers of hours the pizza shop is open. So these are what are corresponding to our red function, which here, let me even do that in red. It'll probably make more sense. So these 3 are what are included in that red. And then our purple, we still have to kind of include that 3 because we're still touching it. So here, I'll put it about halfway through. We all go all the way until that 6th hour right there. And then for that final one, we are looking at from kind of 6-ish until that 12. So hopefully that makes a little bit more sense when I kind of box them in like that about why we're including stuff where. Okay, so now we're going to determine the equation that represents each piece of the function for a given time period and show your work. So from 0 to 3 hours, so on our table, that's from 0 to 3. So that's the first little chunk that we've been looking at. And that, so how we're going to look at these, we're going to first find our y-intercept, which in this case, our y-intercept is 0. And then our slope, and our slope in this case was 30 because we increased every hour by 30 pizzas sold. So for this case, our equation would be y equals 30x plus 0, or just y equals 30x. So the y-intercept's where we started down here, and then we went up by 30 every hour, which you can see on the table and you can also see on the graph. So that's for that one. And then from more than 3 hours to 6 hours. For this one, we are going to look at the point, so that one right there, which is 3, 90. And our slope here, we went up by 10 every hour. So our slope, excuse me, our slope is 10. And we are basing that off of, so we're going to start here at this 390 point. And we're going to go with our slope being 10. So we would end up going down to 82 or 280. Let me say it that way instead. And then what would be 170 and 060. So if that line were to continue, our y-intercept here would be 60. So for our equation, we would have y equals 10x plus 60. And we got that plus 60 from taking our slope down each time to get to 0. Okay, so then the last one we're going to look at is from more than 6 hours to 12 hours. So if we're looking at that on our chart over here, we'll be looking from where 6 to 12 is. So for our slope, the point that we're going to be looking at right here is that 6, 120. And our slope here, if you remember, we were adding, 40 pizzas every hour. So we're then going to go from that point of 6, 120. We're going to go down 40 every hour that we go down. So to get to 5, we're going to have to go down 40. So that'll give us 80. To 6 would be 40. Oh, shoot. Oh, no, not to 6. That should be to 4. To 3 would be at 0. 2 would be at negative 40. Keep wanting to go up, not down. For 1, we'd be at negative 80. And for 0, we'd finally be at negative 120, which is what's going to give us our y-intercept being negative 120. So our equation would be 40x minus 120. So that right there would be our equation for this part of the line. And then finally, we're going to write that. So to write a piecewise function, you must write the equation followed by its domain for each piece of the function. Complete the functions by transferring the information from questions 3 into its proper format. So as you have above on all your papers, we're just going to copy those equations down here. So the first one that was from 0 to x to 3 is going to be from 30x, and that was the equation that we got there. So, and then the next little part was where we were looking at where 10x plus 60, and that was from 3 until 6. And then the final piece that we came up with our equation for was where we had 40x minus 120, and that 6 until 12. And then to define our variables, x here was the number of hours that our pizza shop was open. And our f of x was for the total number of pizzas sold. So, and then we're going to talk about what pieces should be used to determine the y-intercept of the function. And that should always be determined with the y-intercept of the function, because this piece crosses the y-axis and has 0 in its domain. So determine the y-intercept of the function because this piece, the I becomes 40. This piece crosses the y-axis and 0 is in its domain. So in the next, we're going to have y'all use some technology to graph your function and answer each question and identify the piece of the function you use to explain your reasoning. Okay, so now we're going to use technology to graph our functions and answer each question and identify the piece of the function used and explain your reasoning. So I already went ahead and graphed this in Desmos for us, and I'll even show you over here I did it. So you just put like y equals and then the equation that we got that was right here. So we're going to put in these equations and then we'll put in these numbers with those x's as I did here. So you just got to do the little curly brackets and type it in like that and you're good. So we have our whole graph here and we were asked to find at what time of day the pizza shop sells its 300th pizza. So the number of pizzas are, let's look back, was the f of x, which is also known as our y. So we'll go over to our y-axis, go over to 300, and look right here, and let's see if I can get it right on 300. 300. So at 10.5 for the number of hours at which our pizza shop has been open. So it would be between 10 and 11, and 10.5 is between 10 and 11. So it would be 10.5 hours since the pizza shop opened. So what time of day will the pizza shop sell its 150th pizza? So we'll go back to our graph, look at 150. Let's see if I can get it. Oh, so it's 6.75. There you go. So hopefully y'all saw that. So it's at 6.75 hours. And then the 70th pizza, let's go back to our graph. So we're 70. Okay, so 70 is kind of hard to get right on, but I'm going to assume that it is going to be like 2.3. If you can get the exact value, you can put that in your notes, but it's right there around 2.3 hours. So, and then we're going to look at the graph that shows the percentage of charge remaining on a cell phone battery over time. So this time we're interpreting the graph of a piecewise function, and this is what our graph looks like. So describe the type of function shown in the graph. So this graph is representing a linear piecewise function. We can look back earlier in our PowerPoint. I think it's, so a linear piecewise function is a function that can be represented by linear functions only. So this function is just lines. That's all it is. So that's how we determine that. And then we can write a possible scenario that models this graph. So we're going to assume that our cell phone battery started fully charged. And it was used until 50% charge was left. And then it wasn't used for a couple of hours. And where I'm getting at is so that the battery was consistently going down and then it didn't go down at all for a couple of hours right there. So, and then the cell phone was used again and it continued to be used. So the battery continually went down. And then finally at about 16 hours, the cell phone was plugged in. Plugged back in. You can see how the battery power went right back up, so that means that it was charging again. So that's one way to look at it. There's probably 1,000 different ways to come up with a scenario for that, but pretty much the phone was used, the phone's battery stayed the same, it was used again, and then it was plugged in. So now we're going to explain how you know the graph represents a function in terms of this possible situation. Then write f of x to model the graph. Define your variables. So the graph represents a function because at any time the battery has one and only one charge. So like, for example, here at 4 hours, that's the only charge we have. It's kind of like the vertical line test here. So at any point, you're only going to have one amount of battery for that time. So the vertical line test proves that. And it also proves that the graph represents a function. The function that we're going to model this with is, we're going to do f of x, but x is our time in hours. And f of x, which is also represented by our y, is going to be the percent of charge remaining. And so we're then going to go from here to kind of get the variables. Okay, so the first part that we're going to look at is part A. So in for part A, our y-intercept is at 100. And then for our slope, we're going to take this point right here and this point right here. And the difference for our y values is going to be 50 because we're going from 100 to 50. And then we're going from 0 to 3. It's actually negative 50 because we're doing 50 minus 100 over 3 minus 0. And that is how we're getting our slope here. We're just taking the 2 points and getting our slope. So for A, we would be looking at negative 50 divided by 3x plus 100. And that is for when 0 to x to 3. So jot that down really fast because I'm going to have to erase this to go over it again for the B part. So let me get that erased. Dang it, I was hoping it'd go a little faster. Okay, so for our next part, for our B part, because that's just a line that is at y equals 50, that's all we need. And we just need to recognize that it's from 3 to 8. And so 3 is not included in it because if we were to put this on a table, we are still continually going down at 3. At 3 is where we stop going down. And then we stay at 50 all the way until 8 ends. So that's why 8 is included. Let's see if I can get our C. Maybe we'll be able to fit C right here. So we'll put B here. See if we can get C here. So for C, let's look at our points right here real fast. So this is at 8, 50, and 16. We're going to go with it. That is at 16. It's about halfway down. So we're going to go 25. So then we're going to take those points. So we're going to have that 25 minus 50 and 16 minus 8. And that's going to end up giving us a slope of negative 25 over 8. And then we can take that slope. And we can go up 25. So we're at 50, 60, 70, 25. And go over 8, and that would be our y-intercept right there. So for the y-intercept, we would be looking at positive 75. So we would have, and that's not y equals, that's our y-intercept down here. So we're looking at negative 25 over 8 times x plus 75. And then try to jot all that down really fast. I'm going to go ahead and erase the B up here so that we can do our final part of the graph, our D. So pause it if you need this, but we're going to keep going. Should have made about 8 different slides for us to do this on. So for our D, we're looking at a point right here of 1625, I believe it was, and 20, 100. So our slope here is going to be that 100 minus 25 and 20 minus 16, which is going to end up giving us 75 over 4 for our slope. So we can go ahead and start down here. So 75 divided by 4x for our slope. And then we can just take that information and work backwards, and you will end up that your y-intercept would be negative 275. So now that we have all of those, I am going to rewrite all of this on this one slide so that you can have the final f of x for this. So if you need these, pause it real fast. So, but our final f of x here is going to be that negative 50 over 3 x plus 100. And that was for when it was between 0 and 3. Then we had 50 for 3, 8. That negative 25 eighths plus 75 for 8 through 16. And then that's 75 for when from 16 to 20. So that ends up being all of our equations there. So now we are going to talk about how we can determine when that cell phone was not in use. So which part what that was. So the cell phone was not in use when the battery was saying the same. So that is going to go with part B. So the cell phone battery was recharging. So the only part at which we were recharging, so our battery was going up, was part D. So the cell phone was in use. That's when our battery was going down. So that is going to be piece A and piece C. So the cell phone battery is fully charged, and that was at the beginning of A. And it was also at the end of D, because that is the 2 points at which our Y was at 100. So now we're going to look at the cell phone battery was half charged. So that's when we were at 50%. So we got that here. And then we also got that on D kind of about halfway through. So all of B, and then about halfway, part of the way through, on D. The cell phone battery died after 20 hours. So this is where we would extend our graph and keep going, and at 20 hours, we were at 100%. So we can tell that that is false, because if we were dead, we would be all the way down here at 0, where we would need to be, and we are all the way at the top. So that statement is false. The cell phone battery lost 25% of its charge during an 8-hour period. So this one is true. So if we were to look at the 8-hour period from 8 to 16, that was only 25% of the charge, because it went from 50 to 25. So that was 25% of its charge. So that part was true. The cell phone was used the most between the 16th and 20th hours. So again, that is false, because the phone was charging. Our battery power was going up, not down. The cell phone battery was charged twice. This is also false because here our battery's going down, our battery's going down, our batteries stay the same. And this D is the only part where we charged. So it was only charged once. So after 3 hours, the battery had half the charge it began with. And that is true. So after the first 3 hours, so it ends right here. And we are at 50%. So that is true. So you can go ahead and write a scenario to model your own cell phone use during a typical day. If you're a distance learner, you're obviously not going to have a partner to give it to them to graph with. So we're just going to keep on moving. Okay, so now we're going to do some transformations of some piecewise functions. So you can use what you know about transformations to transform any function, including a piecewise function. So a transformed function is often written using the prime symbol, which is shown right there. It's just a little, kind of like an apostrophe. So for example, a transformation of the function f of x is written as f prime of x. So let's go ahead and look at these. So the graph of a function z of x is shown. Sketch the graphs z prime of x and z double prime of x. So when we get down here and we start looking at z prime of x, this is very similar to what we did the other day with absolute values, but it's that plus 3 here. So you would do what we have done in the other day with the absolute values, and we would just take the points on this graph and move them up 3. So we would take 0, 0 and go up to 0, 3. Hang on, let me grab a different pen because, of course, my pen went out again. So, like I said, we would take 0, 0 up to 0, 3. And then we would take 1, negative 1 up to 1, 2. Gosh, guys, I'm sorry. Maybe if I zoom in, this will get better. Let me erase those points, kind of. So we took 0, 0 up to there. And then we took this 1, negative 1 up 1, 2, 3. We're going to take this 3, negative up 1, 2, 3. And let's also take this negative 2, 2 up 3. So I'm going to need to kind of scroll up with my graph a little. So 1, 2, 3. So then you would just draw the graph exactly as it was, which in this point needs to go up 3 as well. Shoot, that's not up 3. So 1, 2, 3. So pretty much I would just graph all of your corners or parts where your graph turns and you'd be good. So let me zoom back out. And then for B, we're looking at where it's minus 4. So you would do the exact same thing, but we would go down 4 from each of those points. So, and we'll do this one in purple. So we're going to go down 4 from each of those. So we're going to take this point right here and go down 1, 2, 3, 4. Down 4. Down 4. Down 4. And then down 1, 2, 3, 4 again. So and then exactly draw the graph exactly as it was. And don't forget your arrows. I think I forgot the arrows in my last one. But so it's the exact same thing that we've been doing, just this time it's with a different function. So again, I would just kind of graph the points at which your graph changes and draw it as exactly as you saw it. So, and then this time we're inside. So hopefully remember the insides, we are going to go left or right. So, and I like to think the opposite, but you can, so our literal C value here would be that negative 3. And our literal C value here would be that positive 1. So for that, and for me, I like to think opposite. So I would think up here that we're going to go left 3, and down here I would think I'm going to go right 1. And that's when I'm looking at what is inside what is written, not looking at my literal C values. So we would do the exact same thing as last time, and we would move this entire graph left 3. And again, I would kind of do the points where your graph turns. So I'm going to actually graph A in red. So we would go over 1, 2, 3. I'm going to go ahead and start drawing it so I don't get confused. And I would take this one left 3 again. I would go up, and then I would go down here and look at this one, and this is, so we'll be right here. And that's roughly that one. And then we'll change into green to graph B this time. So this time we're going to go right 1. So right 1, right 1, and right 1 again. And as y'all can see, we're getting the exact same graphs. It's just doing what we did with the absolute value and going left or right. So same thing again, you would just move these graphs left and right. So now we're going to look at a special type of piecewise function, and as you can read down here, we're going to consider the graph f of x equals the absolute value of x. So we're going to explain how this graph also represents a linear piecewise function. So we know that this is also a linear piecewise function because it's made up of 2 linear functions. And that's that left piece and that right piece. And they each correspond to different parts of the domain as well. So there is x values and y values for these points. So then we're going to write a piecewise function to represent this graph. So we could write that as f of x equals, and this might help some of y'all with your graphing too. So our slope over here is 1 because we go up 1 over 1 every time. And that is when x is greater than or equal to 0. Sorry, that's the bell. And then on the left side, it's negative because we're going to go up 1 and left 1. And that's when x is less than or equal to 0. So how is the symmetry of the absolute value function related in the equivalent linear piecewise function? So as we've talked about several times, how we're always going to get a v, if we were to draw, I'm going to do this in red so you can really see it, down this y-axis right here, if we were to fold it right there, our graph is completely symmetrical on both sides. If we were to fold it on top of each other, you would get the exact same graph. So this is symmetric across our y-axis. So let's then look at number 4. So now we're going to consider this one and we're going to sketch this graph. So to sketch the first part, so that goes from negative 50 to 0. So I'm going to go up to 0 because that's where we're going to cross that y-axis, and I'm going to plot that positive 50. And then I'm going to use my slope, which is positive 1, that's understood to be out here. I'm going to go down 1, over 1, down 1, over 1. And our graph should look something like that. Hey, that's pretty good for me, at least on this little tablet. So, and then when we get greater than 0 is when we start having a negative slope. So we're going to go like that. That line was not as good, but we go down 1, right 1, down 1, right 1. And that gives us our graph there. So explain how the graph also represents a linear absolute value function. So the graph is still V-shaped. So it is V-shaped. And our absolute value function we already described was linear because it's two linear functions up here. Then we're asked to write g of x as a linear absolute value function. So if we were looking at this absolute value, so our typical absolute value, and I'll graph it in green, would be at 0, 0, and our slopes would be like that. So we're going from 0, 0 up to 50. So we would add our d, right? And our d value here would be 50. And then once we got up to 50, say that we were graphing this. I'll graph it. So if we were at 50, we would look like this. So what's our difference between our yellow and our red graph? And that is a reflection, which is caused by a negative out in front of our absolute value. So g of x equals the negative absolute value of x and then plus 50 on the outside. All right, so for the talk, we're going to be piecing all together. So scan the QR code. I forgot to put a link in here. I will put the link on Kiddom so that y'all can click on the link if you can't access the QR code. And this is doing the talk, which is also on page M3-50 in your textbooks. And you are going to want to be, you're writing a piecewise function to model each absolute value function on those. So write the piecewise function to model the absolute value images that appear. If your images do not appear, refresh your page. It should not submit it. And then once you're done with that, come back to this PowerPoint and check out your homework. So if you are in second, third, or fourth, I want you to do number 1 that is on M3-51. So just complete all the pieces in number 1, so A, B, C, D, and E. And this time you are going to have to write this on another sheet of paper. If you want to take a picture of your table that is in the book, you can do that as well. But complete all of those. And then if you're in 5th or 7th, you're going to again complete all of number 1 on the practice. And then on page 52, if you were to flip over, there's a stretch. And I need you to complete 1 through 3 for both of those graphs, graph A and graph B. And please have that turned in to Seesaw before your next class period. If you have any problems or any questions, email me. We can set up a time to Zoom, or maybe we can figure it out over, actually don't email me. Use the Remind app. I get back to those a lot faster and I see them a lot sooner. So send me a message on Remind if you have any questions.